Okay, welcome to the next lecture in number theory. Today I'm going to talk about the fundamental theorem of arithmetic, which just says every integer n is a unique factorization into primes. So first, let's just define what a prime number is. A natural number n is prime if the only divisors of n are 1 and n. And we will note n cannot be 1. 1 is not a prime number because you won't have unique factorization if 1 is prime because you can just have multiple powers of 1. So we're not going to consider 1 as a prime number. So this is what a prime number is. And we're going to go and prove this using induction. So let me first state what induction is. So if we have that P of n is a statement about if P of n is a statement about, or just a statement, could be about the integers or something, and if P of n is true, if this implies that P of n plus 1 is true, and if P of 1 is true, then P of n is true for all n and n. So the classical way to think about this is, I like to think about dominoes. So if you have a bunch of dominoes, if you knock one over, you'll knock the rest over. Because if P1 is true, then this implies that P2 is true. If P2 is true, that implies P3 is true, and so on. So we can actually prove this. And we'll do this using the well-ordering principle. So assume for sake of contradiction that the hypotheses hold and P of n is not true for some n and n. Now consider the set X, which is the set of natural numbers such that P of n is not true. We note 1 is not in X since we assumed P of 1 is true. Thus, by the well-ordering principle, X has a smallest element. Let's call it little x, or m. So P of m is not true, but P of m minus 1 is true. Since we assumed m to be the smallest element, and m minus 1 is an integer, and since we know 1 is not an x, we know m minus 1 is greater than or equal to 1. So we know P of m minus 1 is true, but since P of m minus 1 is true, by assumption this implies P of m is true. But this implies that m is not in x, so this is a contradiction. So from this, we just proved the statement of mathematical induction. And there's also the statement of strong mathematical induction, which you can prove very similarly, where you assume that every element less than n is true implies that P of n plus 1 is true as well. So we will use this to prove the fundamental theorem of arithmetic. And before doing that, we will do the following. So we'll prove the following proposition. If we have an element A that divides a product B times C, and the GCD of A and B is equal to 1, then A is going to divide C. So how can we prove this? We can use the extended Euclidean algorithm. This tells us that there exist integers m and n such that 1 is equal to m times A plus n times B. Now, we know that A divides BC. So let's multiply everything by C. So this gives us that C is equal to MAC plus NBC. But since A divides BC, we know that BC is equal to A times K for some K in the integers. So we can rewrite this equation as C is equal to M times AC plus N times AK. Factor out the A times MC plus NK. So this just says that A divides C. So we just showed that if A divides BC and the GCD is 1, then A divides C. So now we can do this in the following way. Kind of a corollary of this. If P is prime, and P divides A times B, then P either divides A or P divides B. And the proof of this is, since P is prime, the only divisors of P are 1 and P. Positive divisors, I should say. So if P divides A, we are done. If P does not divide A, then the greatest common divisor of P and A is 1, so P must divide B, just using this previous theorem up here. So namely, we have that if P is prime and P divides a product of two elements, then P either divides A or P divides B. So we're now working our way to this fundamental theorem of arithmetic. So now I'm going to give the following proposition. if n is greater than 1, then n has a prime factor. So there's some prime that divides n. So let's give a proof of this. So how can we prove this? So let's just say if n is prime, we are done. So it suffices to show that n is not prime. So what we can do is we can say let x be the set of integers greater than 1 such that n has no prime factor. And we want to show that this set is empty. So what we can do is we can say let x and x be the smallest element. This is the well-ordering principle. And we know x can't be prime, because if it's prime, it has a prime factor, namely itself. So we can write x is equal to a times b, where a and b are not equal to 1. So namely, a and b are less than or equal to x. But this tells us that a and b are not in x, so namely a has a prime divisor, p, and since p divides a, that tells us that p divides ab, which is x. So p divides x, and we get a contradiction. So this implies that x is the empty set, i.e. every natural number has a prime divisor. So we've just shown that every natural number has a prime divisor. So let's keep going. So if we look at the statement of the fundamental theorem of arithmetic, we have that there's a unique factorization into primes. So there are two more things we need to prove to get this. The first is every integer or natural number greater than 1 can be written as a product of primes. So here's a proof, and let's do this. I think we can do this by induction. So for induction, we need a base case, and the base case is n equals 2. And n equals 2 is a product of primes. So now we need what we call the inductive hypothesis. So let us assume that if we assume that every integer k between 1 and n can be written as a product of primes. And so here I'm using strong induction. So rather than assuming that Pn minus 1 implies Pn, I'm assuming that Pk for k less than n, and in this case greater than 1, I want to show that that implies Pn. So our inductive step, we want to show that n is a product of primes. So how can we do this? So there's two cases. Case 1, if n is prime, then n equals n is a product of primes. And case 2, if n is not prime, then n is equal to a times b for some a and b between 1 and n. So by the inductive hypothesis, a and b are a product of primes. Say a is p1 times p2 times pk, and b is q1, q2 times ql. So then n, which is equal to ab, is p1 to pk times q1 to ql is a product of primes. And this concludes the inductive step, because we showed that if we assume for every k less than or between 1 and n, we have a product of primes, then we showed that n is a product of primes. And so by induction, we have shown that every natural number greater than 1 is a product of primes. So, yeah. So now, the last part of the fundamental theorem of arithmetic is the uniqueness part. For n greater than 1, prime factorization is unique. And let's go ahead and prove this. So let's say, again, let's do this by strong induction. So the base case is n equals 2. This is uniquely factored, since there's no other way to write a prime number as a product of two elements, since its only divisors are 1 in itself. So now, let's do the inductive hypothesis. This says that, so let's assume for k between 0 and n, that k has unique factorization. And then we have the inductive step. This is going to be the exact same thing. So we want to show n has unique factorization. So we again have two cases. If n is prime, it is uniquely factored. Now, case 2 is probably the more interesting case. If n is not prime. So what we can do here is we can write, so say we have n is, so n is we know by the previous proposition, say n is a product of primes. So say n is equal to p1 times p2 all the way to pr, but it's also equal to q1, q2 all the way to q sub s. So we want to show that each of these factorizations are the same. So let's pick p1. Okay, so kind of the claim here is that p1 divides q sub so let's also make it so that they're strictly increasing. So I claim that p1 divides q sub 1. So we know p sub 1 it divides this entire product, right? So since it's a prime number and it divides a product of primes, then let me try and say this correctly. So again, we have to do some sort of, I guess what's going to happen here is we have another kind of induction per se. So if p divides this, then either I'm just going to say p1 divides q sub I for some I. If p1 divides q1, we are done. Otherwise, the GCD of p1 and q1 is 1, so p1 has to divide q2 times q3 all the way to q sub s. And then if we induct on s, because if p1, if the product on the right only has a single term, then we're done, because if p1 divides q1, then q1 divides p1, since they're both primes. And yeah, so you can then induct to get that p1 divides q sub I for some I. And we can always rearrange terms. So let's just assume p1 divides q1. And that's what this ordering will actually end up doing. So then what happens is if we look at n divided by p1, this is equal to p2 times pr, which is equal to q2 all the way to qs. But we have that n over p1, this is strictly less than n. So by the induction hypothesis, n over p1 has unique factorization. So we have this factorization here and this factorization here are the same. So namely, so r equals s and qi is equal to pi. And this is for I equal to 2r. But then this implies that n equals p1. So this implies that our factorization up here, p1 to pr, q1 to qs, has pi equal to qi for each I equals 1 to s or r. And so we get the factorization is unique. And so this proves the fundamental theorem of arithmetic. So yeah, that is that. Something else we could talk about is, so we talked about GCD, and we could also talk about the least common multiple of A and B is equal to the smallest, and here we're thinking positive, number C, such that A divides C and B divides C. So what we could do is, if we have A and B are natural numbers, then A times B is going to be the GCD of A and B multiplied by the least common multiple of A and B. So here's one way you can kind of do this, is if you take A, right, so if you take the factorization of A and the factorization of B, so let's factor them as follows. P1 to the E1, P2 to the E2, PR to the ER, where the PI are distinct, and B is also equal to P1 to the E1, P2 to the E2, PR to the ER. So the PI are distinct, and the prime factors of A and B. And the EI are 0, 1, and so on. So here, for example, if we take, say, 12 and 15, so if we think of 12, this is 2 squared times 3, because it's 4 times 3, but we're also going to think of this as 5 to the 0. And 15 is going to be 2 to the 0 times 3 to the 1 times 5 to the 1. So the entire idea behind having this factorization involving both of the prime factors but allowing 0, because anything to the 0 is 1, is, if we look at the GCD of 12 and 15, this is going to be 3. And the least common multiple of 12 and 15 is going to be 60. And one way you can do this is 3 is 2 raised to the minimum of 0 and 2 times 3 to the minimum of 1 and 1 times 5 to the minimum of 0 and 1. So, and similarly, this is raised to the max. 2 to the max times 3 to the max times 5 to the maximum. And this is kind of how you can get this. So that's kind of the claim. And so if we can show that this fact that the GCD of these two numbers is the product of the PI's raised to the mins, and the LCM is the product of the primes raised to the max, then if we look A times B, it's just P1 to the min times P1 to the max times Q2 to the min, or P2 to the min, P2 to the max, and so on. And that's one way you can see the statements follow from that. So this is P1 to the min, or PR to the min, PR to the max, and all the mins is the GCD of A and B, and all the maxes is the LCM of A and B. So, what we should prove is that this, so we need to prove this. GCD of A and B is the product of PI to the max of, oh, maybe I shouldn't have done EI here. Maybe I should do D of EI and DI. Because they'll have different exponents. And we note that, so observe that the product of the PI to the max of the DI and EI, this divides A and B, or wait, this should be the minimum. So GCD, you do the minimum, LCM, you take the max. This is just because, well, it divides A because each of these prime factors divides A. So, maybe I should say something. There might be a little proposition. So we talked about GCD, but and we talked about how it's the greatest common divisor, but you can also say the GCD of A and B is equal to C, where if we have some factor D that divides A and D divides B, then this implies that D divides C. So, since in a way you can see this is, if D is a common divisor of A and B, if D does not divide C, which is the GCD, how can we do this? So we could appeal to So, so we note that a common divisor, just using this up here, a common divisor of A and B, well, it has to have pi, and the largest the exponent can be is the maximum of EI and DI. So, that's one way you can see the GCD here. And so if D is a common divisor and it doesn't divide, so I'm kind of using this observation. So this tells me that this product of the PI to the min divides the GCD. And also the GCD is going to divide this product of the min. And this is because if we look at the greatest common divisor, every common divisor has to divide, each PI has to divide, can have the largest power of the PI can be the minimum of those two for it to divide. And similarly for the max. So this proposition here wasn't necessarily needed. And you can also, but just note, if D does not divide C, then there's some prime factor of D that does not divide C, if you know this, and thus you can get a contradiction. So let me kind of get rid of this because we don't need this. And we can also just say, observe that A and B divide the product of the PI to the maximum of DI and EI. So this should be min. And this is because you can only add powers. And this is the smallest possible way you can do it, because you need that for it to be a common multiple, that each of these PI has to have at least a factor of the maximum. And so this is one way you can see that the product of two integers is the greatest common divisor times the least common multiple.